Alright, everyone. So, in the last two videos, we saw the cases where our characteristic equation to our second order linear homogeneous differential equation with constant coefficients had two unique or distinct real roots or two complex roots, right? Okay, so this time we're going to look at the very last case, which is when the equation has a single, one repeated root, and it's going to be real if if all our coefficients are real of our differential or characteristic equation. So we're going to assume that. So we'd have one real repeated, right? So one real repeated root. It's going to be repeated two times. All right. So let's talk about what happens then. Basically, let's say that our characteristic equation, it's a, again, like the previous two videos, it's am squared plus bm plus c, right? That's equal to 0. Okay. And let's say that as the topic of this video goes, let's say that this characteristic equation has a single root that's repeated two times. So m, let's say okay, so it's just gonna be one root. I don't need to write m1 and m2 because they're basically the same. Okay, so m1 is the same as m2, right? Or two solutions if m1 and m2 are two solutions to this equation. So I'll just write that as m. Yeah, I'll just simply write that as m. We have our solution to our characteristic equation. Let's try to plug that in our general formula for second order linear homogeneous T. Where was that? Yeah, this one. Let's try to plug that in here. Okay, so actually, let's say that m, that's basically m1 and that's basically m2. So you get what I'm trying to say. Both the roots are the same. So we'll just plug those in. We'll just plug those in into our solution equation. It's gonna be y equals c1 e to the power m1 multiplied by x. So one of the roots will, both of them are the same. So m, multiplied by x plus c2 multiplied by e to the power m2 multiplied by x. But again, m1 m2, they're the same. Okay, they're the same. So I'll just write m multiplied by x. All right. So we see that we have a factor of e to the power mx in common. So just to simplify that, we'll write c1 plus c2 e to the power mx. And c1 and c2 are just some arbitrary constants. So obviously their sum is also going to be just some arbitrary constant. We'll call that c. Okay. So this should be equal to c e to the power mx. C e to the power mx. Well, so at a first glance, it looks like we found our general solution. It's much simpler than the other one. So it's kind of like an added bonus. Nothing seems to be that wrong. It seems to be going better than expected. But the problem here, there's a major problem here, is that our this characteristic equation obviously came from an equation like a y double prime plus p y prime plus c y equals 0. Okay, so as I have already said a countless number of times, we are dealing with a second order equation. We're dealing with a second order differential equation. The highest power, not the power, the highest derivative here is the second derivative. So that's why when you find the general solution to second order differential equation, it must have two arbitrary constants, and it should need two subsidiary conditions to solve for it, to find the particular solution. That's why, again, m is actually not unknown. That just is just a solution of your characteristic equation. So m is not unknown. You actually have only one unknown here, that's c. Okay, where you are actually supposed to have two unknowns. This being a second order differential equation mandates you to have two arbitrary constants or unknowns in your general solution. So us having one constant right here is actually a problem. I mean, one arbitrary constant. So how do we deal with that? How do we fix this general solution? One thing I'd like to be clear is, since this was a solution, m was in fact m1 and 2, they're basically the same as m, and this was the solution to our characteristic equation. Okay, by the logic from from I guess three or two videos ago, when we basically derived this formula, this general solution formula. It's not like that solution is invalid. Okay, it's not like that solution is invalid. That's definitely a valid solution. I'm just saying that it's not the complete, general solution. Okay, so this definitely has to be part of the solution. This is valid. Okay, so this is one portion, and the way we find the general solution is, okay. So we say, okay, so this is some constant c multiplied b to the power mx. I'll just modify that a little bit. Little bit. So let's say some constant d multiplied by e to the power mx. So not that different. You might be wondering if it really leads to the same thing, why am I even doing it? But well, the small modification here is we're also gonna multiply by x here. We're also gonna multiply by x. Okay. So this is the other solution that I'm adding. As we know, the homogeneous equation, the sum, this if this is a solution and this is a solution, the sum is also a solution to the differential equation. This is the other portion, just a bit modified from this, that I'm adding to make this the general solution. So we can actually again factor out e to the power mx, but unlike before, where it's not going to be reduced to just one arbitrary constant or anything. So now we have two arbitrary constants. C and D. Now this at least has the form that we might say that okay, so this might be our general solution. And now I'm definitely sure this is a burning question inside you. What's the whole wait, where did it go? What's the whole logic behind this? What's the whole logic behind introducing this term? I just brought it out of thin air. Well, the proof is just a bit involved, and I'll actually do it at the towards the end of this video. So for those who are really interested in it, please do stick around till the end and watch that proof. But if you'd like to just pass that next exam and you don't really care that much, you can just take this solution and say, okay, so this is what I do, when I have when my characteristic equation has repeated roots, the same repeated root. I just find that one solution and I plug it in here. It's gonna be e to the power that one solution multiplied by x, and this term is multiplied by a general linear term in x. Okay, some general linear term in x, so which is some constant plus again some constant multiplied by x. Anyways, so this is basically what you do when you have repeated roots. So let's actually try our hands at some problems. The first one I have here is, let's see, 9y double prime minus 24y prime plus 16y equals 0. And I also have some initial conditions. They are when x equals 0, when x equals 0, y is equal to 5, and y prime is equal to 7. Alright, so let's try to solve this equation. Okay, so you again might be able to guess from how this video is going and from the title itself, but this is gonna have repeated roots. But again, we're not gonna just do assume that on a whim. Let's actually find the characteristic equation. This is gonna be 9m squared minus 24m plus 16. Replace y double prime with m squared, y prime with m to the power 1, just m. Y you don't need to replace with anything. It's basically the 0th power of m, which is just 1. Okay, so 16, that's gonna equal 0. Okay, so this you can solve using the quadratic formula, and you can also solve using factoring. We can just notice here that 9m squared is actually just 3m whole squared. 16 is just 4 squared, and minus 24m is 2 multiplied by 3m multiplied by 4. Okay, so this matches that form, our a minus b whole squared expanded out, that form. It's a squared minus 2ab plus b squared. Okay, so we can actually factor this and write this is a whole square, so this is 3m, this one minus this one, so minus 4 is equal to 0. Well, this squared equals 0 means the term inside has to be 0. Okay? So 3m minus 4 being equal to 0, 3m minus 4 equals 0, or m is equal to 4 by 3. M is equal to 4 by 3. There's one thing I'd like to say. It's probably obvious, but most of the time when we're solving differential equations and we need to find some algebraic solution, something like that, like solution to our characteristic equation or some other thing, most of the time, if possible, we just leave it to our calculator. So the way I do it in an actual exam, or when I'm doing some assignment or anything, I just plug the quadratic in my calculator and let it do its job. So let's see. Now we have the root. Now we have that single repeated root. We will just plug that in our general solution equation for this case. So it's gonna be e to the power that root multiplied by x. So e to the power, so our general solution, so I'll write general solution. Okay, so general solution is y equals e to the power that root, which is 4 by 3. 4 by 3 is our root, so 4 by 3 multiplied by x, and this is going to be multiplied by some general linear term in x. So I'll just write that as ax plus b. All right, so this is my general solution. Okay, but now we have two initial conditions. Let's use them. First one is when x equals 0, y is equal to 5. When x equals 0, y is equal to 5. So if we substitute that, what we get on the left side is obviously 5. On the right side we have a multiplied by 0, that's just 0, and e to the power 0 is just 1, so we only have b multiplied by 1, so that's just b. So we already have the value of b, that's equal to 5. Okay, so now let's try to solve for a, and for that we'll need to use the other condition. Let's see. That one is when, again, x equals 0, y prime equals 7. So the derivative of y, first we need to find an expression for the derivative, so let's do that. If y is equal to this, y prime is gonna be, first let's differentiate this, keep that the same. So let's see, it's derivative of that linear term is gonna be just that constant a multiplied by e to the power 4 by 3x, and we're gonna keep the linear term the same and differentiate this. So differentiating this, the 4 by 3 will come out of sorts. So 4 by 3, okay, so let's see, ax plus b multiplied by 4 by 3 e to the power 4 by 3x. Now when x equals 0, we know that y prime is equal to 7. So let's substitute those numbers in. So let's see, when x equals 0, obviously y prime is said that's equal to 7. This one is just gonna be 1. E to the power 0 is 1, so 1 multiplied by a, that's just a. Actually, yeah, I don't know why I'm still writing b. This is we found that that's b. Sorry, that's 5. Okay, so well, that one's done, and then we have plus. Well, this is 0 again. This is 0, and this is just 5. 5 multiplied by 4 by 3, and this is again just equal to 1 e to the power 0. So 5 multiplied by 4 by 3 multiplied by 1. Don't need to write that. So our value of a is gonna be, let's see, I'll actually, for convenience's sake, express 7 as 21 over 3. Okay, and this is obviously 5 multiplied by 4 is 20, so 20 by 3. So we have 1 by 3 left over. All right, so our particular solution, or given our initial conditions, our particular solution to a differential equation is y equals a, so which is 1 by 3 x plus b, which is 5. Okay, e to the power 4 by 3x, and voila, we have done all that we were told to do. We first found the general solution to our differential equation, and then we plugged in the initial conditions to find our particular solution. Actually write that. So this is the particular solution, and this is basically how all these problems really go. And this is the last case. Yeah, now if you have watched all the 3 videos, you fully know how to solve any second order linear differential equation with constant coefficients. Okay, whether it has two real distinct roots, whether it has two complex roots, or whether it has one repeated real root. You can solve all those equations now. All right, so that's some cause for celebration. Now, I'd like to actually do a similar problem as what I did in the last video. It's the reverse type of problem. Let's say that you have some general solution given to you. So this is y equals some constant c1 x plus some constant c2. Okay, e to the power minus 5x. This is the general solution to some differential equation. Now we need to find the differential equation. So again, as is obvious from what you have been doing until now in this video, this is your case when the second order linear different homogeneous differential equation with constant coefficients, which has the characteristic equation has repeated roots. So where did I write all that stuff? Okay, so now all that we need to do is first find that repeated root. Okay, then derive our quadratic characteristic equation, and then just write our differential equation. All the steps in reverse. So as is obvious from here, this one, it's actually pretty obvious to find which one is our repeated roots. It's just this one. It's just the coefficient of x on top of e. So minus 5 is our repeated root. So m equals minus 5, okay, is our repeated root. Now there's a couple of ways you can think about how to make the quadratic out of this. You could say m plus 5 is a factor of our quadratic, a quadratic that's going to be in the characteristic equation. Or I could do the same thing as I did in the last video. All of them are really more or less the same. I'm bringing this to that side, adding back to both sides. Now I'm going to square it. I need a quadratic. My characteristic equation needs to be a quadratic. So m plus 5 squared is going to be 0 squared. That's obviously 0. And so m plus 5 squared is m squared plus 2 into m into 5. So that's 10. That's 10m plus 25 is equal to 0. Okay, now all that I need to do is replace the m terms by by the respective derivatives of y. So m squared is obviously going to be replaced by y double prime. 10m, that's obviously m is going to be replaced by y prime. So y prime here, but plus 10 here as a multiple. And also you have 25, and 25 has that invisible 1 multiplied with it, and so you're going to have 25 also y multiplied with that. Okay, the zeroth derivative. Okay, so this is going to be equal to 0. All right, so this is my differential equation. It's pretty easy. Voila, we have also solved this. Now this is really more or less what all that you need to do to solve this differential equation. And all the cases where for second order linear homogeneous differential equation with constant coefficient. So this is just something for us to reflect and all. But we have covered all the three cases. So this one's check. So now as I've said in the beginning of this video, this theorem didn't the general solution here didn't actually come out of thin air. There is a proof for it. Okay, so I'll actually attempt to do that now. The major reason I actually put it off for the end of the video is it uses one method which I haven't shown it before, a method for reducing differential equations. So I haven't exactly shown that yet, but I hope that you can follow me. I'll try to do it as simply as possible. Let's actually talk about how to do this. So our as we saw, our characteristic equation, it's gonna be am squared plus bm plus c equals 0. Okay, now we said that our roots obviously gonna be the root for this is gonna be given by our quadratic formula, right? It's gonna be actually I'll just I'll write this on the side because we're gonna use this a couple of times in this group. It's a fact that, as we know, since we have a single repeated root, our determinant is 0. B squared minus 4ac is going to be equal to 0. It's going to be equal to 0, nil. All right. So let's see. Going back to this, our roots are gonna be negative b plus or minus b squared minus 4ac divided by 2a. But what did we just say just a while ago. Well, our determinant, which is b squared minus 4ac, this is 0. This whole thing is 0. Okay, so this term doesn't matter. Though your root is gonna be as expected. You have only one root. It's gonna be negative b by 2a. Negative b by 2a. All right. So our as we have discussed, I think 2 or 3 videos ago, if this is if this is a root to the characteristic equation, even if it's just one root, given that it's a root, this has to be a solution. This has to be y equals e to the power this root. Okay, this root m, m, this root m multiplied by x, and m we already found, that's negative b by 2a. So negative b by 2a multiplied by x, this has to be a solution of my differential equation. We at least know that it's a solution. That much is certain. Now what I'm going to try to do is multiply a function of x here. Okay, multiply some function of x. Let's call that okay, so let's call that w. Let's call that w. It's some function w, okay, of x, and I'm gonna say that this is gonna be my general solution. What I'm trying to do is find some function w, okay, some function w, which is gonna which is, if I write it as like this, if I multiply w with e to the power minus b by 2a and multiply by x, this is gonna be my general solution. Okay, this is gonna be my general solution to my differential equation. Now, this might seem a bit new, but it's valid. As I'm already only saying that I'm gonna try to find a function like that, which makes it the general solution. We might or might not be able to, so I'm just gonna try. And to be honest, we can at the very least we know that this w of x will have at least some form of kind of solution, because as I've discussed in in that video about linear homogeneous equations, if e to the power minus b by 2ax is a solution, I actually discussed it here too, at the very least we know it's not invalid. Our some constant c, actually did I remove that? Okay, so some constant c, let's see, some constant c multiplied by e to the power negative b by 2a. So this is has to be a solution. This has to be a solution, and based on that theorem that I talked about in that video about linear homogeneous differential equations, if you have some solution, so if this is a solution, some constant multiplied with that's also going to be a solution. Okay, and also if you add any other solution to that's also going to be a solution. Okay, so this is definitely a solution, as I've said quite a few times. So if we just pattern match, at the very least y, not y, w of x, it will have a solution like this. It will have a solution w of x equals some arbitrary constant c. At the very least it has to have that solution. Okay, hopefully it has even one more arbitrary constant. So if that happens, we can rest assured about this being our general solution. Well, anyways, so that's the theory behind it. We at least know that this is not something invalid. So we're going to try to find some w of x so that this becomes the general solution. Okay, so let's try to do that. Well, first thing, we have y, and the thing is we need to substitute y and its derivatives, from this right here into our differential equations. First, let's find the derivatives. So if y, y equals w of x multiplied by e to the power this thing. So our y prime, or derivative of y, it's gonna be, well, I'll omit the x from here, writing that over and over again. So let's use the product rule. Again, need to be careful that w isn't a constant necessarily. This is a function of x. So first differentiate that and keep the exponential term the same. So w prime e to the power negative b by 2ax, and then differentiate the other thing and keep w the same, plus w negative b by 2a e to the power negative b by 2a. So we can simplify this a bit. We can factor out e to the power, that's this exponential. I'm gonna call this exponential from now on, because it's quite tiring saying it in full. So if we do that, if we factor out the exponential, so we get w prime from here, and negative b by 2a multiplied by w from here. So negative b by 2a multiplied by w, and this is all multiplied by the exponential. So now this is my y prime. Now we also need the second derivative. Our differential equation has second derivative too, so we need to find that. So for that, we just differentiate both sides of this. We differentiate both sides of this. Obviously, on the left, we're going to have y double prime. On the right, we're going to have, let's see. Again, first differentiate this, keep that the same. So let's see. It's going to be w double prime minus b by 2a, it's just a constant, and w prime. All right. And this is multiplied by the exponential. And also, what we have, we will differentiate this, keep that the same. So what we'll have here is w prime minus b by 2a, w, okay, multiplied by negative b by 2a, e to the power negative, basically the exponential. So now we'll again, do the factoring as we did before. If we factor out the exponential from here, what we're gonna get is, let's see, we have w double prime. That's the only second derivative on the right side, so it's w double prime. About w prime, we have negative b by 2a, okay, as the coefficient. Also, again, another negative b by 2a, so it's gonna be negative b by a. So negative b by a, w prime. And with w, what we have is b squared divided by 4a squared, plus b squared divided by 4a squared, so minus plus, so b squared, okay, multiply these things, basically this and this, so b squared divided by 4a squared, multiplied by w. So this all is again multiplied by the exponential, b by 2a, b by 2. Okay, so I'll actually rewrite that a bit. See, so b by 2ax. Okay, so we'll substitute all of that into our exponential. Substitute, not our exponential, our differential equation. Our differential equation was obviously, as we've seen before, ay double prime plus by prime plus cy equals 0. Okay, now let's substitute the expression for y prime, since that is the comes at the head. So a, and we'll have the expression for second derivative. So w double prime minus b by a. Actually, let me just copy that. And this is the expression for the second derivative. For the first derivative, again, I'll do the same maneuver, you could say. So also we have the expression. Finally, we'll have the expression for y itself. It's gonna be c multiplied by y is basically w, as we defined it, w multiplied by e to the power negative b by 2. All of this is gonna be equal to 0. Now all we need to do is what happens here. One thing we can do is actually from all of this we can factor out e to the power negative b by 2ax. To be honest, we can also divide it on both sides, because we know that it's never going to be equal to 0. So actually, I'm just going to divide by it. Okay, we're going to divide by that. Okay, and just say, okay, that's gone, spoof, that's discarded. Okay, so with that out of the way, what we're going to have, all the other things. So what we have here, I'll also try to collect the derivative terms. Okay, so the only second derivative term of w is this one. Okay, it's this one. So let's see, that one's a w double prime. Okay, for w prime, what we have is a multiplied by this, so it's basically negative b w prime and then plus b w prime. Okay, so what we have here is, that's interesting. I think you can see how things are simplifying. So negative b w prime plus b w prime. Now this is basically 0. We don't need to write that. And also the last one, so we have dealt with w, I will dealt with w prime. All that we need to deal with is w. So that one is b squared. Okay, so a multiplied by this, so b squared by 4a. Okay, that's one coefficient. Also negative b squared by 2a, negative b squared by 2a, and plus c, we'll write that. So b squared by 4a, negative b squared by 2a, right? I hope I'm remembering correctly. So yeah, negative b squared by 2a plus c, so plus c. Okay, so this one, yeah, we can actually simplify this a little bit. So b squared by 4a minus b squared, b squared by 2a, that's just gonna be negative negative b squared by 4a, 4a. Now plus c, now this doesn't, this might seem a bit familiar. If it doesn't, it will be if I factor out negative 1 by 4a, negative 1 by 4a from the thing in brackets. So obviously I'll have this outside right here. If I factor out negative 1 by 4a, from this expression right here, which is this plus c, what I have here is, let's see, b squared, okay, b squared, and this is basically gonna get multiplied by negative 4a, so minus 4a multiplied by c, and then we have w. Yeah, I think most of you are really excited to see this. We again have our determinant popping up here, b squared minus 4ac, and we know that our determinant is 0. We already said that this has repeated roots. Okay, so our determinant is 0. This expression cancels out. This completely cancels out. All that we have left is a w double prime is equal to 0. So, and we can divide by a. A is just, and this is also important that one assumption, and I've already, this is the assumption for this is an assumption for the whole second order linear homogeneous differential equations themselves. For them to be second order, a cannot be 0. Okay, your a cannot be 0. So obviously we can divide by that. That's no problem. So all that we have left is w prime. W prime is equal to 0. W prime is equal to 0. All right. So if that is the case, okay, we can actually just solve this. We can actually just solve this by integrating 2 times. We can actually solve this by integrating 2 times. If we do that once, if we take the antiderivative of both sides, on the left we'll have w prime. I only need to add the constant on one side. On the right, we're gonna have let's say some constant. I'll call that a. Some constant a. If we then again take the antiderivative here, on the left I'm gonna have w. On the right, what I'm gonna have is this constant multiplied by x. Okay, so obviously integration of a constant is that constant multiplied by x. Then again we need to add another arbitrary constant. Let's call that b. Now we have the solution to w. This is exactly what we were aiming for. We have the solution to w. And what happens if we substitute that into that expression, that general solution expression that we were trying to find, that we assume that this is going to be my general solution. We'll try to find a solution of w. This one is w multiplied by the exponential, right? So w multiplied by the exponential. So y equals this term, which is any general linear term in x multiplied by my exponential, which is basically here you have your repeated root. Okay, your repeated root, that multiplied by x. Okay, all that is on top. This is my general solution. We have completely proved that this is my general solution when we have repeated roots in a second order linear homogeneous differential equation with constant coefficients. Okay, so that is enough for this video, and I hope you found it at least a bit helpful. And if you did, please do leave a like and subscribe to this channel. So I'll see you next time when we'll actually discuss how to find the solution to any nth order linear homogeneous differential equation with constant coefficients. That's hopefully the next video. Might be a bit long. So yeah, see you later and study smart.